If we have a vector in the plane, there are two ways that you can define what this vector is. You can define this vector in terms of its magnitude, which is just the length of the vector, and we denote magnitude by putting these double bars around our vector, and in terms of our angle. So if you're given the magnitude and the angle, that defines the vector completely, because it gives you how long it is, it gives you what direction it's pointing. The other way to define a vector is in terms of its components. And its components, when to find the components of the vector, you're breaking it down into the x part of it and the y part of it. This is our x component, this is our y component, and then the hypotenuse is our magnitude. So the other way you can give a vector is as an ordered pair inside triangle brackets. So these are the two different ways a vector can be represented. In physics problems, typically you'll be given magnitude and direction. You'll be asked to report an answer that's of magnitude and direction. But in order to do the math in the middle, you need to use component form. So we need to be able to translate quickly between these two different ways of representing a vector. And doing that is relatively simple. If you're given components, you can see from this triangle I've drawn that we can find the magnitude of the vector simply by using Pythagorean theorem. The magnitude of the vector is the x component squared plus the y component squared, square rooted. And that the angle we can find with a trigonometric ratio. Tangent is opposite over adjacent. So take the tangent of theta, it's v sub y over vx. So to get our angle, we take the inverse tangent of the y component over the x component. So that's how we can get from component form to magnitude and direction. Go the other direction, we can also use trigonometric ratios. If we look at our triangle, the sine of theta is opposite over hypotenuse. That's v, the y component, over the magnitude. So if we're given magnitude and direction, we can find our y component just by multiplying the magnitude by the sine of theta. And similarly, we can find our x component by multiplying the magnitude times the cosine of theta. So in component form, that gives us magnitude cos theta, comma, magnitude sine theta. Do a couple of quick examples of going from component form to magnitude and direction, going from magnitude and direction to component form. If we're given a vector in component form, remember its magnitude. To find the magnitude of the vector, we simply use Pythagorean theorem. So the magnitude of the vector is square root of the x component squared plus the y component squared. 5 squared is 25, 2 squared is 4, it's root 29, which we can punch into our calculator and get 5.385, etc. And our angle, the direction angle theta, we can find by using arctangent. Arctangent of the y component over the x component. And again, we can just punch that into our calculator, and this comes out to about 21.8 degrees. Over here, if we're given magnitude and our angle, then we can find the components by using trigonometry. Our x component is the magnitude times the cosine of our angle, and our y component is the magnitude times the sine of our angle. And again, we can simply punch those into our calculator to get that for cosine 78 is about 0.832, and for sine 78 is about 3.913. Since I haven't given these to you as physical quantities, we're not worrying about significant digits for the moment. But that's how you go from component form to magnitude and direction and back. Now, both the examples I did before had angles in the first quadrant. when you're in a different quadrant, it can get a little bit trickier. Now, in math class, in pre-calculus, when we learned about vectors in different quadrants, we typically used the angle from the positive x-axis. In physics, however, a lot of times we're given directions in terms of north, south, east, and west, or angles from the horizontal if we're working with a horizontal and vertical kind of problem. And for that reason, in physics, typically when you're given an angle or when you're reporting your answer, we don't use this angle. We use the reference angle. Whatever angle in math we call that theta prime, in physics we're just going to call it theta, but we usually use the angle from whatever acute angle the vector makes to the x-axis. So in this vector, our theta would be this angle. Now, that means that we're going to need to use a little bit of reasoning rather than just punching things into our calculator in order to work out some things having to do with signs that are attached to the vectors. So if I tell you that this vector has a magnitude, we'll call it vector v, this vector has a magnitude of 5, and I tell you that this angle it makes to the x-axis is 48 degrees, then you can calculate your components. But you're going to have to think a little bit before you just punch things into your calculator. So our x component, we know, is our magnitude cosine theta, and our y component is our magnitude sine theta. However, if we punch these in, these will give us both positive numbers. And two positive numbers is a positive x component, positive y component, which is a vector in the first quadrant. This vector, obviously, is not in the first quadrant. This vector is in the third quadrant. And to make this vector, the x component is to the left, the y component is down, which means that we need to attach minus signs in front of both of these. And that's a little bit of thinking that you don't have to do. If you use this angle, the signs take care of themselves. But in physics, we generally use that acute angle and then attach the signs based on our reasoning. The same holds true if you're going the other direction. If I tell you that this vector, its component form is -1, 6, well, the magnitude of it, if I call that vector u, the magnitude, you can just find using the same method we've used before, using Pythagorean theorem. And that's 36 plus 1, that's root 37. But the direction you have to think about a little bit again. So we use that theta is the arctangent of the y component over the x component. And if we punch that into our calculator, that gives us, what the calculator spits out is minus 80.54 degrees. Now, clearly, if we're measuring an angle from the x-axis up to here, that should be a positive angle. The reason this is negative is because tangent, if you remember back from trigonometry, tangent is negative in the second quadrant. In order to report this angle, what we will do, we will ignore the sign. We simply say 80.54 degrees, but then we have to say what that's relative to. This angle is moving upward from the x-axis, but it's in the negative direction. So we go down the x-axis to the left, and we rotate up 80.54 degrees. So we say that's 80.54 degrees above the minus x axis. So you have to think a little bit in order to figure out how you're going to report that angle. And as you may have noticed as I'm doing all of these problems, we always do report those angles from the x-axis, because then we can stick with the standard cosine for the x component, sine for the y component. Now, in physics, most of the problems we do are word problems. You'll be given a situation, and you'll have to do calculations with it. In this case, we have a man who's walking south by 28 degrees west at 5 miles per hour. Write this as a vector in component form. Now this is how we're typically going to represent angles when we're given a problem in terms of north, south, east, and west. So if we draw this, typically following the pattern that is established on most maps, we say that north is our positive y direction, south is our negative y direction, east is our positive x direction, and west is our negative x direction. And what this south by 28 degrees west means is that you start at south and you rotate 28 degrees toward the west. So I go south and I rotate 28 degrees toward the west, and this is our 28 degree angle. If I said if it was east by north, we would start at east, rotate however many degrees toward the north. If it was north by west, we would start at north, rotate toward west. Now, what's tricky about this, let me write that 28 a little bit bigger. What's tricky about this now is that to use our standard sine, cosine, cosine for the x component, sine for the y component, we always had an angle from the x-axis. So you have to be careful of that. You can't always just directly punch in the angle that you were given. Now our angle from the x-axis, this is 28 degrees. Our angle from the x-axis is the complement of that, which is 62 degrees, just taking 90 minus 28. Once we have this, we can just punch our numbers in to figure out, punch our numbers in and apply the appropriate sign to figure out what the component form of our vector is. First off, our x component, we take the magnitude times the cosine of theta. Our x component is in the westerly direction, which we say is the negative x direction. So we apply a negative sign in front, take our magnitude, multiply that by the cosine of the angle from the x-axis. Similarly, our y direction, we're going south, which is the negative y direction, so we put a minus sign out front, magnitude times the sine of our angle. And then we could simply punch that into our calculator to get what those values are as decimals. This is a word problem going in the opposite direction. We have a woman, she walks 2 kilometers east, then 4 kilometers south. We want to write this as a magnitude and direction. It's always a good idea in physics to draw a picture. So if we draw our set of axes, she walks 2 kilometers to the east, 4 kilometers south. So her displacement vector looks like this. Now, this is 2, this is 4, and following our pattern, we can find the magnitude of our vector simply by using Pythagorean theorem. Square root of 2 squared plus 4 squared. That's 4, that's 16, so this is root 20. And you can pull out a root 4, which gives you 2 root 5 kilometers, is the total distance she has moved from her starting point. Now to find our angle, we always want that angle from the x-axis, and that is simply the arctangent of 4 over 2, which we can punch into our calculator and determine that this is about 63.43 degrees. But how do we report that angle? Well, that is the angle where we go east and rotate toward the south. And therefore, we say that it's a magnitude and direction. This is 2 root 5 kilometers. We're starting at the east. So we say east by 63.43 degrees, and we are rotating toward the south.